Another session. So today we're continuing our review of kinematics. So far what we have done is we decided we've defined a frame uh, and then in that frame we define how to do position r of some point P if r a function t, and then these are vectors, and then we have did what's called displacement delta r, which stood for q is a little bit later minus rp, which is r at t plus delta t minus r at t. So and you have to look at videos before to go in more detail. Just I'm trying to list what we did to save time. And then we say velocity at instant t was v was dr dt, which was a collection of like a dx dt dy dt dz dt. This x, y, and z are the components here, x, y, z for the position. And then we talked about also speed at instant t, and we just turned out to be speed was ds dt, and s was distance along the trajectory or path of motion. And then we did define what acceleration was, which was acceleration was just taking another derivative. So dv dt, and you put this inside here, which is the second derivative of r with t. And these are abstract. You can't really, there's no way to take a vector and take an derivative of it. So you think of this as dvx dt dvy dt. Then you can calculate dvz dt. And what is this vx, vy, vz? They are basically this. So this guy is that guy is that, etc. And take a derivative of that. So we had a constant velocity motion. Go back to a previous video. Then constant speed motion. These are very important. Okay. So now today we're going to do constant acceleration motion. Constant acceleration motion. So constant acceleration motion is constant acceleration motion is a very interesting concept. So we're going to do analytically. We are thinking of acceleration is constant. So so let's denote constant by some a0 vector. So what I mean by this is a of time t is a0 independent of time. okay, what does it buy us? Well, so we look at what a0 must be. This is a vector, so it must be some a0x, a0y, a0z, and this is basically dvx dt, dvy dt, dvz dt, right? So when we make it equal, we mean this is equal to that, this is equal to that, and this is equal to that. So we get three equations which are very easy to solve. Okay, so like let's solve one of them. So derivative of this equals to a constant, we're calling this value. An example will be like, okay, I have a dvx dt is 3 meter per second square. So how would we solve this? Well, you just bring this on the other side, and so vx dvx will be 3 dt, ignoring the units, okay? And then you do integration on both sides. Here t is the variable, so let's call 0 to some arbitrary time t. So this will be what the value of the vx is at that instant. Let's call it vx v0x, let's call it v0x, and vx at that instant. So this will give me vx at that instant minus v0x equal to 3t. So that's how it's going to work in the numerical value of v0x, a0x. So over here, you can just carry out the same thing, and so this will give me vx at arbitrary instant minus v0 at 0 time equal to a0x times t. So this is from 0 to t I did. But if you say t1 to t2, you can do it for any time. So this will be vx at t2 minus vx at t1 equals a0x times t2 minus t1. So if you did that, you'll get this. So mathematical is very easy. So a of t equal to a0 means I'm going to be able to vx, I'm going to use this. Vx at t is equal to v0x plus a0xt. Vy of t at t will be v0y plus a0yt, and the z part at instant t will be v0z plus a0zt. Well, why stop here? You can further solve this guy for the position with time. So like write this guy as dx dt. Now this is a known number. So for instance, if v0x will be say 5 meter per second, then this will be vx of t minus 5 equals to 3t, or vx of t equals to 5 plus 3t. So let's try to see how much progress we can make in this direction to get x coordinates. Okay, we can make a lot of progress. So we can write this as dx dt. This is some number, initial is x part of the initial velocity, and this is just a constant. So v0x plus a0xt. So again, we send this on the other side, so this becomes a dx is v0x plus a0xt dt. Looks like today there's some work going on outside our house. There's a lot of noise there. I'm sorry about that. I'm also like multitasking right now, so there's some other program running in the background, so they maybe make some sound every now and then. All right, so we do this, and then suppose I want to go from 0 to some instant, arbitrary instant t. Then, so because of this is the t, these are the things I'm interested in. So for that, it will be x at 0 time, and this will be x at instant t. And this normally people write down x of 0. So this will be x of t minus x0. If you do this out, I'm going to leave that alone. I'm going to get half a 0x t square. So you can see I can send this down as x0 is where it was at 0 instance. That's given to us. So we just, from there, we can actually find out where the x will be at any instant. And there's nothing stops us from doing this other guys. Y of t equals to y0 plus v0 yt plus half a0 yt square. And you can just go down the line with the z direction. Z of t equal to z0 plus v0 y z t plus half a0 z t square. So this has led to these 6 equations. These are 3 equations here has led to equation 1, equation 2, equation 3, equation 4, equation 5, equation 6. And that's all you can do. So that's what constant acceleration motion will give you. Okay. Now there is this motion called vertical motion near Earth is an example of a constant acceleration, and it is a one-dimensional problem. So let's do that out. So now I'm going to do 2a, which is going to be vertical motion near Earth. So by saying vertical motion is only interested in up and down motion, okay? So normally people say, oh, here is the origin and I'm going to use y coordinate up. Of course, there's the x coordinate here and z coordinate. So we're going to using this coordinate system means x at all time going to be 0 and z at all time is going to be 0, and only thing non-zero for an object is going to be y. So at some instant is going to be y of t, and we're going to have to find y of t. Maybe it was at some other instant, this was y at t equal to 0, which is y0, which is also written as y sub 0. So those are the values. This is given, and we need to find this, and we also need to find what is the y velocity at instant t. So these are 2 things we would be able to find. We are interested to be in vertical motion, and so the only thing is this would, of course, this will mean for all t. This is symbol for all t that's the case. So this just means Vx part will be 0 and Vz part will be 0. And of course, this also means a x part is 0, a z part is 0. So the problem here is going to be y motion. It's a vertical motion near Earth. If we put one more information, we say that in this motion, acceleration is pointed down. So acceleration is pointed down, and value of the acceleration with the value of the acceleration is g. It's not minus g, it's because it's positive. So this motion, which is y of t, vy of t, but ay is going to be, if this is going to be positive y is pointed up, then this says the ay will be minus g, with g taken as is 9.81 meter per second square. But this is not the same everywhere on Earth. So this probably getting so close to this, not so important. Often I'm going to use 10 for this value, but it's hardly 10 anywhere on Earth. It's not 10, but this is but 9.8 whatever, okay, is so this is like a little uncertain wherever you, but in textbooks this is the number that people use. Okay, but this is a positive, and this minus is coming because the direction. You gotta know. So y is minus. So let's call it, this is y and this is x. So what you do is just remember, if this x and this y, suppose you had a position vector over here. This is O. This is your r vector, and this is a y equals to -5 here, -5 here, okay, +5 here. So what is this position vector would be? Remember last time I told you, every vector you gotta go back and look at what the position will do. If the question was about position vectors, in the position vector you have no trouble saying r will be 0, -5, 0, no trouble whatsoever, right? You're gonna say the y equal to -5, x equal to 0, and z equal to 0. You would have no trouble whatsoever. Then you got to do exactly the same thing. Draw this vector, which is the acceleration due to gravity. There's a name for this, acceleration due to gravity. And so when we acceleration like this, we say, if you just have this is the acceleration, then you say we are doing what's called free fall.
Partially filled.
Free fall, okay? This is free fall. So if it's a free fall, even it's going up, even when the object is moving up, we say free fall. So say if this object is going up and they eventually come down, but even this motion is called free fall, not just this part, okay? All right, so let's look at, we've on the vector part, going back to the vector part. So we draw the vector like that. And this arrow is, because this is the acceleration arrow, the size of this is g. So this is the acceleration arrow. This arrow is acceleration arrow. So if I were to write analytic part of this, of course, it has no x and no z parts. So this is a sub x, this is a sub c. So what should go here? Well, look at this, it's going to have to be minus g there. That's why it's minus g. Okay, so obviously we can use the same equations, except now for a0 we have 0 minus g 0. It's not a new thing. We have already done constant acceleration. This is constant acceleration. So if you look at this, this would be not there, this wouldn't be there, and this will be minus half. Minus g. So we're going to get, therefore, we are going to get Vx at t will simply be V0x. Vy of t will be V0y. And that's going to be minus g times t. And Vz of t will be V0z. That's it. So there's no acceleration for the x part, no acceleration for the z part, only acceleration is affected y part. So this 1 equals to 1, 2, and 3. So let's call it 1, 2, and 3 again. 4 will be just x of t will just be V0x. Sorry about that. x0 plus V0xt. 5 will be, this guy will just be y at instant t will be y0 plus V0yt minus half g t square, and 6 will be just z of t is z0 plus v0z t. So people can memorize these. It has these guys have, all of them have t in them. I mean, from this, all of these have t in them. All of them t, and you can try to eliminate t. For instance, you can get t from here, for instance, and can eliminate t. Okay. Often what people say, this functional thing, don't just suppress this. So people say, oh, suppress, they don't write this. Too much cluttering notation. I understand when I just write without 0, I'm talking about at arbitrary time, that time given like that. So often you want to memorize, you want to memorize this if for, so you don't have to do integration everywhere in your life and you encounter a problem with a constant free fall. So this is the case, okay? So because x and z are 0 for 1D just going up or coming down, or so it can be motion go up, maybe, so this one kind of motion, just fall, another kind of motion, maybe you like go up, start here but end here. It can be start here but end here. So all these possible interesting scenarios you can get just vertical motion. Of course, in the present case, this is all 0, this is all 0, this is all 0, 0, 0, this is all 0. Then you have just these two equations. Okay, let's look at those two equations. So Vy equals V0y minus gt, and y equals to y0 plus 0 yt minus half gt squared. So you can solve this for t. So t will be this minus this, Vy minus V0y over V0y minus Vy. So bring this on this side and bring this on that side, so this Vy. And if you do this in here, you go to y, let's call y minus y0 together. So V0y, V0y minus Vy over t minus half g V0y minus Vy square over this over g. So this, you can see these two expressions will combine. So let's expand this out. V0y square minus V0y Vy. This let's g y minus y0. So multiply by g both sides. So just keep the other parts. Half V0y square minus plus V0y Vy minus half Vy square. So this got cancelled out, and this half of that went away. So this is half V0y square minus half Vy square. So what you get, multiply by 2. So this make 2 times g y minus y0, and so you have this equation which no t, so I call it no t equation. Very good equation. Bring this guy on the other side, rearrange it. V square equals V0y square minus 2g y minus y0. This is another very important thing to memorize, is the so-called no t equation. But actually this just came out from these two. So these are only two equations that you derived, and from there you can kind of manipulate to get t, remove t. Okay, let's do a numerical example of this before I get too far. So an example will be like, I toss a ball with, say, 20 meters per second. So question would be, and several questions you can ask. Where will it be at t equals to 1 second? What is it? What is, if this was y equal to 0, initially is t equal to 0, 1 second. Another question will be, what is t when it gets to all the way to the top, where Vy has to be 0 because it will be come to rest before turn back. So y it has to be 0. Let's look at this, plot this guy. If I plot Vy with t, says some positive value, 20 meters per second, and with this is going to have a negative slope. Let's start with here. This is 10 meter per second and 20 meter per second. So it's going to have a slope and it's going to continue. So there will come a time it's going to become 0. This is Vy is 0. So slope is minus g according to this equation. So this is the top. At the top point is going to have a zero velocity. So you can ask those questions. Let's pick one. Let's pick this question. How high it will go. Okay, so this is say h, and how much time it will take to get there. Oh, all right, so if this is my initial and this is the final, let's take those two for this question. So initial to final. What do we know? We know v 0y is plus here 20 meter per second, and we're already using this equation because it's just a gravity thing. So we want to get we already know this, we know this, Vy is 0. We need to find that, and we already, so we don't need to use, we just know t equation. So 0 equals 20 square minus 2 times 10 times h, because y minus y0 is h. This is the y and this is the y0. So y minus y0 is what we are calling h. So this just tells me h is also 20 meter. Just cool, right? So how about time? Well, if I know, I can use for time, I can use either this or this, but this one looks like much easier to use. So for time it will be V0 is, this is 20 minus 10 time, so t equals to 2 seconds. Well, let's see, where will it be, what will be this h at 1 second mark? Where will it be at 1 second mark? And how fast it will be going? This kind of question. So now in the same situation you have the same initial segment, but this one is, let's call it the second final. So we are looking at this now. So initial to second final, this segment. In this segment, what do we know? We know V0y is the same, 20 meter per second, but this is not the same. Vy we don't know. We don't know little h, we don't know. H, which is still y minus y0, because this is now new y. Okay, let's call it y2. Y2 minus h0. And so with this common mistake here people make, but we do know time, which is same as t minus the 0, that's a segment, and that's given to be 1 second. All right, so we just pick whatever will help us. So this does involve t, so can't use, no t equation is not going to be useful. This will definitely give me Vy. So Vy equals V0y minus gt, and V0y is going to be 20 minus 10 times 1 is 10 meter per second. And we can use this one, y minus y0 is h. So y minus y0 is equal to v0 yt minus half gt square, and v0 is 20 times 1 minus half times 10 times 1 square is 15 meter. So looking back at this problem, it was very interesting to just redraw it out. So this was 20 meter, this is y, this is 10 meter, and this is 0. So at t equals to 2 seconds was here, but t equals to 1 second, it's here. Of course, it's slowing down. That's going to go less and less distance with time, right? And eventually it comes to stop. But at this point, at the very top, you have y is equal to 20 meter, t equals to 2 seconds, vy equal to 0, but ay is not 0. Actually, ay is minus g. And because this is not 0, the next instant it will start to fall. And this is crucial. Even if this is 0, it looks like if it's 0, it's not going to go anywhere. But it is going to start to change the very next instant. Because of this, vy will be negative. So like in very next instant, it's vy will be pointed down. So if you look at y, x, the vy vector when it's coming down will be some value, maybe minus 1 meter per second. Then v vector is 0 for vx, minus for vy, and 0 for z. So that's where next instant I'm going to pick up and become negative. Till then, vy was positive. This was positive just before it came in, not that value, but just before it came in, it was pointed up. So just before it's coming in, it was pointed up. Of course, at this point, it was going 10 meter per second. So at this very instant, if it was like, say, 1 meter per second, then if this was the v, then that v will be 0 for vx, some value for a, let's say 1 meter per second as an example, and 0 like that. So that's why if the velocity is pointed down and the y-axis is pointed up, you get a -1. All right. So that's a kind of trivial example. So next sort of example is where, let's go back here, where at least we use this part. Okay, we look at a motion in which you have both x and y going on, but no z going on. Okay, so next lecture, next will be motion like x, y, kind of like that. And so for this motion, z equal to 0. But I think this video has come very long, and I'm going to postpone that discussion of this motion. And this is this is called projectile motion. we are going to talk about that. Here again, I'm going to ignore air resistance. We are ignoring air resistance completely. I forgot to mention that. Here the acceleration again will be, no matter where you are, say time t, the acceleration is pointed that way and is 0 minus g 0. Okay, so acceleration still will be constant, and it's only this vector, and y-axis pointed up will make this representation this way, and we will have z equal to 0. For that, you have to wait for the next video. Okay, see you in the next video. Bye.